Okay, so in this question, we're given the equation, and this is the Raymond Davis John Bacall experiment equation, where they took a tank of dry cleaning fluid, which was basically a compound of chlorine, and they were hoping, and what actually happened, they worked out that what would happen basically was the neutrinos, the electron neutrinos released by the nuclear fusion in the sun, would come along, go to the bottom of this deep mine in North Dakota into this tank of dry cleaning fluid, and the neutrinos would interact with the chlorine atoms, and they would deposit energy to the chlorine atoms, and that would result in them becoming in undergoing a nuclear reaction to become argon atoms with the release of an electron. And then they basically separated the argon atoms from the chlorine, counted the number of argon atoms, and as a result of that they could figure out how many neutrinos had interacted with the chlorine, and therefore gain information about the electron neutrinos coming from the sun. So what we're going to do here is we're going to work out the difference in mass between both sides of this equation, and then figure out something about these neutrinos. Now, what you'll find is the mass of the product is actually greater than the mass of the reactants, and that means that these neutrinos need to have a certain amount of energy in order to make this reaction happen, okay? Because you have to put energy into the reaction to make it happen, and that energy comes from the neutrinos. We've got a slight problem here. This is unusual. You don't normally get this type of question in the exam, but I'm going to show you how to do it I'm going to show you how to do it anyway, okay? So the problem is this: we're given the mass of the chlorine atom and the mass of the argon atom. Now, the mass of the chlorine atom assumes that this has got 17 electrons, and it assumes that this has got 18 electrons. Okay, so we've got an extra electron being picked up on this side. Okay, this electron here is as a result of a neutron being converted into a proton and an electron. So that's okay. The problem is that we've got 17 electrons in this atom and 18 in this one, so they don't balance up. So that's going to mess up our mass calculation, so to speak, because we're going to be taking account of an extra electron. And that extra electron will have just been picked up by the argon atom, because when the argon atom gets produced, or the argon nucleus gets produced, I should say, it will just then, an electron that's floating around somewhere will just be attracted to it, and it will become an argon atom. So that electron's been pulled in from elsewhere, so to speak. So what we need to do is we need to get the mass of the chlorine nucleus and the mass of the argon nucleus, and then we don't need to worry about the electrons. Okay? Now, usually in the exam, you'll be given the mass of the nuclei, and then you don't need to worry about the electrons. That's usually what happens in the exam. But so this sort of calculation that I'm about to show you, I've not seen this on the exam before, but it's useful to know anyway how to do this. Okay? Right, so with all that said, let's do this. Okay, so to start off with, then we need to work out the mass of the chlorine atom. Now we know that the mass of the chlorine nucleus. We know that the neutrino has basically zero mass. Okay, it's a little bit of a simplification, because it has been argued that neutrinos do have a very small mass, but we're just going to assume it's zero here. Okay, so on the left-hand side, the mass on the left-hand side is going to be 36.96590, which is your mass of your chlorine atom. Take away take away 17, okay, electrons, because the atomic number here is 17, so there must be 17 electrons in this atom. So it's 17 times 0.000548, okay, and that's going to give us the mass on the left-hand side, and that comes out as 36.9564 U. Okay, so that's the mass of the left-hand side. Now on the right-hand side, what we've got there is the mass of the argon atom is 36.96677, but we need to take away that from that 18 electron masses to get the mass of the argon nucleus. Okay, but also on the right-hand side we need to add on the electron mass, which is, remember, the electron's produced by a neutron changing into a proton and an electron. Okay, so that's going to be plus 0.000548. Okay, and that gives us this mass, which is 36.957454 U. Okay, So what you notice is, look, this mass here is greater than this mass, as I said. So we can now work out the mass defect, okay? And we'll just do it in the normal way. We'll take the mass of the thing on the left-hand side, whoops, and take away the mass of the thing on the right-hand side. And that gives us minus 0.000870 U, okay? So that tells us that the mass of the product is greater than the mass of reactants. So we can now work out the energy required to make this reaction happen, because the mass is greater here than here, we need to actually put energy into, because the energy that goes into the reaction is converted into that extra mass, okay? So let's work that out. The energy is going to be equal to 931.5 multiplied by the missing mass, or the mass defect in U. Okay, and you could include a minus in there if you want, just to remind yourself that this is energy that needs to go into the reaction. And it comes out as minus 0.810 mega electron volts. So what that means is any neutrino with energy greater than this will make this reaction happen. So this reaction is only sensitive, it's only going to happen if these neutrinos have more than 0.810 mega electron volts of energy. Any neutrinos with less energy than that won't be detected by this reaction. Okay, so there we go.